Hello.
Hello.
Okay.
Go ahead.
Yeah. There I am being presenting here the optimal planning of energy storage system for the semi-urban microgrid, including PV integration. So the objective of this study was to find the optimal location and sizing of battery storage system or typical semi-urban distribution system, considering intermittency of renewable energy sources also. Reducing with this, we have reduced the power loss and improved the voltage profile. Then we have validated the result from the RTDS simulation. We have taken the semi-urban microgrid pilot from the USS to perform the battery optimization process. In this, we have total 25 residential houses which are having solar power of 5 kilowatt peak at the rooftop and the 100 kilowatt hour till 100 kilowatt capacity of battery storage system. The methodology used was brute force methodology. Then identification of a possible location was find out by based on survey, physical survey, and find the locations where we can place the amount of battery we have in the hand. Then generating battery BSC placement scenarios. Different scenarios were generated. Performing power flow for all the above scenarios which were generated in the 4 different operating conditions. We have considered 4 different operating conditions. First is the with PV generation and battery storage system both. Then the second is battery storage system with feed from the one of the feeder pillar. We have 2 feeder pillar which are feeding, and we consider the worst case scenario in which one feeder pillar is delivering the power to whole system. The third scenario is battery storage system with no PV generation. That is the night case, and the same was considered. The above fault at the feeder pillar is considered, and with the no PV generation and battery storage system is delivering the power. Find the optimal battery placement. Then we find the battery optimal placement by objective function value calculation. Then then we generate sizing scenarios for above placement and perform power flow all the possible scenarios with the above 4 operating conditions. Find the optimal sizing based on the objective function value calculation again. Then we validate these results in the RTDS simulation. The objective function which we have formulated considered the total power losses and voltage deviation index, and the while meeting the voltage constraint, power flow, PV constraints, and battery charging constraint, and the load flow. Then the identification of the battery locations. First, we have considered required land area, availability of point of connection, and distance from the point of connection to BAC. So these all were considered, and the possible battery location which we have marked here with the blue battery symbols are total 5 placement where we can place the batteries, and that are FP1A and FP1B and FP2B and FP2C in the system. Then we have find out the 12 placement scenarios for which we have simulated the power flow analysis. We have performed the power flow analysis for different 4 cases. So total there are 48 simulations running for the power flow. Then the objective value were calculated for all the placement and 4 cases. From this we can see that average objective function was minimum at the place scenario number 6, where the feeder placement was at feeder pillar 1B and 2B. So we find the optimal placement is at 1B and 2B. Then then we have to find the after optimal placement we have to find the optimal sizing. For the optimal sizing, we have considered 50-50, then 70-30 ratio, 60-40 ratio of the battery. Then this were run at the total 4 different cases, which is total to 20 different scenarios were simulated through the power flow, and the objective values were calculated. This is the table where the objective values were is displayed. Then in the case 1, we can see that the scenario 1 is the optimal as the objective function is minimum. And case 2, we can see that again scenario 1 is the minimum as the objective function is minimum. Case 3 also scenario 1 is minimum, and the case 4 scenario 4 is minimum, but as the maximum number of times the objective function is minimum in case 1, so we have considered the placement BSE optimal sizing as a case 1 placement combination 1 scenario, that is 60% battery on the feeder pillar 1B and 40% battery on the feeder pillar 2B. Now validation was performed on the real-time digital simulator. In the real-time simulation lab, for the following cases. Battery placement considered for validation. First, we have considered 60% battery on feeder pillar 1 and 40% on feeder pillar 2A, which is not the optimal, and 0.6 battery on the 1A and 0.4 on 1B. And another placement that was found optimal was 0.6 battery at 60% battery on feeder pillar 1B and 40% battery on the 2B. For each scenario, for each of the above scenario, 3 placement, effective battery charging and discharging observed on the voltage of the feeder pillar 1C and 2C, and the load. This is the battery charging discharging effect were seen on the voltage, and another effect was seen using the load variation observed at the feeder pillar 21 and 1C and 2C voltage. So here are the figures, where the figure 1 shows the utility power battery charging discharging, and another and the figure B shows the voltage at feeder pillar 1C and 2C with the placement of 0.6 battery at 1A and 2A. And voltage figure C shows the voltage at 1C and 2C for placement scenarios, 0.6 battery at 1A and 0.4 battery at 1B. And the optimal placement was at the voltage shown is at the figure D, where we can see that voltage do not. Hello.
Yeah, go ahead, Veeresh. Sorry, actually that we admitted.
Okay.
Yeah.
Okay. Observation was that voltage do not fall below the 0.6 per unit at feeder pillar 2C with the optimal placement. Overall voltage profile is better for the optimal location found earlier. And the impact of load variation was also done. And here also we can observe that minimum deviation of the voltage is observed with the optimal placement and sizing, which was calculated from the method. So that's it. And the observation where conclusion method for optimal placement and sizing is presented for the semi-urban microgrid parade, which was under the USS project inside the IIT Kanpur campus. The objective function used for the optimal placement and sizing was formulated depending on minimizing the loss and the voltage deviation. Apart from the technical constraint, implementation constraint like required area and distance between PSO point of coupling and battery system is considered. Optimal location is validated using RTDS.
Please leave your message for 9.
4 different operating conditions. Voltage profile improve with the optimal location and sizing of the BEC. Optimal BEC placement also provide the backup to the sub network independently. Ratio of 2 BEC power rating. The main observation was that ratio of both the 2 battery sizing power rating are found approximately equal to the load in respect to the network. So if the battery is 60% on the subnetwork 1, then the load is almost 60% on the subnetwork 1, and the 40% was on the subnetwork 2. So 40% load was in the subnetwork 2. This is observations. Thank you. Any questions?
Yes, so we have a couple questions in the chat that we have. Can you talk a little bit about the battery chemistry, and what did you use, any standards with battery sizing?
Battery was considered, lithium ion battery was considered, but we have not formulated any kind of chemistry in that, but we have considered as a discharging rate and charging rate was considered. Here is the charging or discharging pattern considered for the battery, which is shown by orange line and the blue line. That's it.
What is the voltage profile optimization equation that you're using?
Voltage profile. Yeah. Here is we have considered the voltage division. So we have considered that the total number of nodes where deviation was sum and weighted with the loss. This both objective were considered, total loss, and this is the voltage deviation at the summation of all the nodes considered. Is it okay?
Ahmed, do you have any other questions?
No, perfect. But
okay.
Did you? But just one question. So, in your optimization method, how do you know what is the location? I did not see anything in the location. So,
location.
Yeah.
For the location, we have go on the physical survey and find out the required land area, availability of point of coupling, and the distance between point of connection and the battery where we will be placing. Here we can see.
So can you use those things in your equation?
No, we are not used in the equation, and we have used for the generating different scenarios just.
So here maybe you have only you have only couple of scenarios.
Yeah, here we have couple of scenarios.
Then how do you do that? If you have many, let's say number of.
Then we have to include it in the method itself. That is, we are not included in right now in these equations.
Okay, thank you. And it is unbalanced, right?
Yeah, it is unbalanced. Yeah.
A, B, C,
yeah.
3 different phases.
Yeah.
Thank you.
So, Ahmad, just I want to add, I'm Srivastava.
Hi, Professor. How are you doing?
Yeah, I'm good. Yeah, how about you? So, 2-3 things. It was lithium ferrophosphate chemistry. That is what we zeroed down, looking at the safety aspect and also cost and everything. And your one question was about charge discharge. Even during daytime, when it is fully charged and solar PV is there, we are intentionally discharging it also. That logic has been put. There is a microgrid controller, and so that the grid supply is minimized. But SOC
is forecasting, because did you also use any forecasting that, let's say I know tomorrow is cloudy. So in that case, do you want to discharge?
Yeah, we have in agenda. We have not used online forecasting as of yet, but that is very much there. The ADMS is being implemented, and we will use that. Yeah.
And I also ask standard. Why? Because I know for lithium, for lead acid battery, there is a standard for sizing, let's say 485 or something. But for lead acid, lithium ion, maybe still there is no standard for the sizing for different type of.
Yeah. So I mean, what we had fixed, we had zeroed down on certain make only. So looking at standard makes. So we have selected only that 4 or 5 mix. Yeah, and we got one.
Okay, thank you, Professor.
Okay, I think we have two other questions.
Okay.
What is the loading? I think Professor Shrivastava may have mentioned, what is the loading during the charging of the battery?
Normally during night time we are charging. During daytime we are charging. So the solar power is enough to supply the load, and then excess power we are using for charging. Yeah. So that logic have been put, and it is also linked to the SOC level. So if it goes down below minimum value, if it is touching minimum value, then it will be charged. Yeah. So that logic is there in our microcontroller. Yeah.
Okay, another question relates to the design of the project. How does the designing, have you looked at considering electric vehicles?
Oh, electric vehicle, the example he gave was only for the lanes actually. Electric vehicle, we have charging stations and supported by solar. So those are separate locations, not in the same ring. So there are 2 locations in the campus which has fast charger, AC slow charger, and actually it is vehicle to grid or the EV to home kind of charger, a smaller rating. But unfortunately, we don't have any vehicle which can support this logic. So, and then EV rickshaw chargers. So there are 2 places we have total 5 chargers at one place. So that is separate. But that doesn't have any battery. So that has solar backup.
Okay, let's see. So I guess the other question is, as you're talking about the optimization of putting the batteries, so what kind of data do we have?
No, here it was residential area, and very few possible locations were there. So what they did, they solved for. Sorry, there is a disturbance in my house. So they solved for only those possible locations, and but the ultimate story is that we had to shift everything to substation, because we had to bring cable from substation here and then take it back, and that was becoming very complicated. So we have shifted both the batteries near the substations. Yeah.
Okay. Are there any other questions?
Professor Srivastava, I have just one clarification. For this equation, I think the student already mentioned. By the way, do you think this equation is correct? VI by Vmax minus 1, the voltage part. I think it should be very close to VI minus 1. That would be good enough. Why do you need Vmax divided by? Your target is to reach voltage maximum. I think it should be very close to nominal voltage, right? So I don't know why we use Vmax, but do you have any reference for this equation?
Yeah,
but okay, we can check that.
Yeah,
we can check offline. Yeah.
Yeah, Varesh, if you want to talk about using that. Did you understand the question? It was going in and out.
Yes.
Okay, go ahead.
It is actually max voltage considered. It should be, I think, minimum.
This Vmax,
I have to see
Vmax
it.
is constant, right? This Vmax is constant, let's say 105, something like that. In India or in USA, it is 105. Is it that, or max voltage of your system?
Max voltage of our system, actually, we have considered here.
Not
I think there is some typing error. This is a V nominal.
Yeah, minimum or nominal.
No, V nominal.
Yeah, nominal will be better, I think.
Minus
Typing
so
mistake
V
might be
nominal is
there.
always 1, right? V nominal is around 1. So then actually even we don't need that.
Right. If it is in per unit.
Yes.
Yeah, if it is in power unit, yes, that's correct. All right.
All right, we've got time for one more question. All right. Well, thank you for Varesh for your presentation. If you want to put your email in the chat, Ahmed can reach out to you, or if he has other questions, as well as others from the top. Thank you.
Thank you.
Okay, so let me get my PowerPoint back. Oops. It's not, there we go. Okay, so our last talk for this evening, or the session number 1, is we have Payush from IIT Kanpur. So I'll turn it over to Payush.
Yeah, Piyush, I think. Piyush?
Piyush? Oh, Piyush, okay.
Okay. Piyush, are you there?